sort of continue our discussion on sort of the introduction to the subject today that we started last time. We saw how basically optical communication systems have sort of slowly replaced electronic and electrical means of communication, especially for high data rates and long distance communication for global connectivity, right? Starting from maybe 50, 60 years ago, optical systems have started taking over. So just like for mobile networks, wireless networks, we have these generations, right? So we started with 1G, 2G, 3G, and now we are using 4G networks, and soon 5G is planned to be launched, right? So similarly for optical systems, sort of there have been generations of development and improvement. Okay, so let's just briefly take a look at how optical communication systems have evolved. So basically here we are plotting sort of the loss coefficient of the typical optical fiber technology for that generation, right, in dB per kilometer. And then on the x-axis we have wavelengths. So the wavelength of operation has also sort of evolved over time, depending on various factors that we'll see. Okay, so here it's a log scale on the y-axis, and then this is the wavelength in nanometer. So starting from sort of visible wavelengths, going up to sort of near infrared wavelengths. Okay, so right, so if you look at so this is responsibility. So units are amperes per watt, right? So that means for a given incident optical power onto the device, it generates a certain current, right? So ampere current per watt optical power. So actually, the first generation optical communication systems could work with just silicon technology, because if you look at the responsibility for silicon, okay, so that peaks sort of roughly near this wavelength. Okay, so this is silicon. So basically for these 850 nanometer wavelengths, one could use silicon photodetectors, right? And silicon technology was sort of already developed and ahead of this 3.5 technology which is being developed, right? So right, so for detectors one should use silicon, but of course you know that one cannot make light sources from silicon, right, because of this indirect band gap. So that's still an open problem, right? One cannot make light sources in silicon. So for sources, basically people developed this AlGas technology. So aluminum gallium arsenide, again based on 3.5 semiconductors, right? So which sort of had this range of wavelengths. Right, so aluminum and gallium are group 3, arsenic is group 5, and depending on the different mole fractions of these atoms, one could tune the wavelength in sort of this range. So these are sources or transmitters, right? This is receivers, and this is the fiber channel. Right, so that's the first generation of optical networks which were developed. Sources based on AlGas, these fibers which had a minimum loss around 850 nanometers, and then detectors based on silicon. Okay, and then so the performance metric sort of which was achieved for this first generation was right about 100 megabit per second data rates over tens of kilometers of transmissions. Okay, so of course by today's standards that doesn't sound like much, but in the 1970s that was already an improvement over, for example, the electrical networks. Right. So then there were improvement made in optical fiber technology. So basically the loss profile went down, and so it sort of now looked like what you might be familiar with from optical fibers. Okay. So the second generation of optical fibers were much better, right? And basically overall the loss was much lower, and also the minimum loss wavelength sort of now went towards infrared wavelengths. Okay. So the second generation of so this minimum sort of occurred around 1300 here, right? So there were two minimums here, one around 1300 and the other around this 1500, 1550. So now you know that modern networks use this band of wavelengths, right? So the second generation used this 1300 range of wavelengths, right? So for that, of course, we can't use these ALGAP sources, or we also can't use the silicon detectors, right? So basically, new technology had to be developed for that. So that technology was based on indium gallium arsenide phosphide. Okay, so now 4 different semiconductors were used. Right, so indium and gallium are from group 3, arsenic and phosphide are from group 5. And then depending on again the mole fractions and the relative ratios, one can tune the wavelength over this range, the near infrared. Okay, so that's for the sources, right? And another reason why people went for this 1300 wavelength was, as you know, we are not plotting dispersion here, but people who've done, for example, the fiber optics course, that for silica fibers, the dispersion sort of crosses 0 around 1300. So the at these wavelengths, the dispersion is also very low, so you can send optical pulses over long distances without them broadening too much. In terms of detectors, again, this similar kind of technology was used. So they are called in-gas detectors. Okay, so for the second generation, which was sort of let's say 80s to early 90s, that time frame, speeds were boosted to greater than 500 Mbps, and distances were also increased to like 40 kilometers. Okay. And then as people wanted to expand the optical networks further and further, right, going towards longer distances, then people found out that actually the minimum loss, so around 1550 here, the loss is even slightly lower than at 1300, right? And that's partly because you have this peak coming here, which sort of increases the loss here, right? And this peak is actually due to residual moisture in the fiber. So absorption due to this hydroxide radical, right? So part of the water molecule. So that has an absorption peak right here around 1400. So the residual moisture, which was already very small, right? I think so much less than part per million. But even that small amount of water, because the rest of the fiber is so pristine and the loss is so low that you can see the loss from that small amount of moisture. Okay, so people found that if you want to go to hundreds of kilometers of transmission distance, then you have to go to a different wavelength. Here 1550, which has lower loss. So the loss here at 1300, let's say, is about 0.5 to 1 dB per kilometer, but here in 1550, one could go down to like 0.2 dB per kilometer. So, right, and one could use the same technology for the sources and detectors. Just you have to use different mode fractions. Right, and of course now dispersion will be a problem, right? Because the dispersion at 1550 for the usual silica fibers that are used would be higher than at 1300. But then people figured out ways to compensate for dispersion. Okay. So this improvement in loss was sort of a big enough gain that people sort of went to this new wavelength of 1550, which is sort of now the in current times also the most widely used wavelength range is this around 1550. Right? So then people were able to enhance data rates to beyond like 10 Gbps over now hundreds of kilometers. Okay, and then to increase distances further, if you want to go to now 1000 kilometers and intercontinental distances, global connectivity, then you have to use repeaters, right? So even for 0.2 dB per kilometer, 100 kilometer means 20 dB loss, right? So that's only 1% of the power remaining. So still you need repeaters, right? And so initially these third generation systems had electronic repeaters. So you detected the optical signal using some photodetectors, get it into the electrical domain and then amplify in the electrical domain and then reconvert to optical. Okay, so this was before the invention of optical amplifiers. And then in the 1990s, optical amplifiers were invented, especially this EDFA, so which worked for this wavelength range here. Right, so roughly let's say around 1530 to 1610. That's the range of this erbium doped fiber amplifier. So now you could remain in the optical domain. You don't need to convert to electrical and optical back, right? And you could now extend the distances a lot without sort of compromising on data rates, because to go beyond this sort of became difficult because of this electronic repeater. Because once you convert to electrical and convert back to optical, you're limited now by electronic speeds, right? So that sort of limited this. So there's a question why dispersion at 1550 is more than 1300. That's just the property of glass, right? So you know optical fibers are made out of glass. So glass has a refractive index which depends on wavelength, right? And dispersion, I mean, we'll discuss a little bit more about dispersion. People who've done the fiber optics course know already, but here we'll sort of recap the important points. So we discussed dispersion in one or two classes. But basically the dispersion depends on the slope of this refractive index, or the double derivative of this refractive index versus wavelength, right? So it's basically, for optical fibers, it's a material property, like how the refractive index of glass varies with wavelength. You can control that a little bit from the fiber dimensions, like what is the size of the core, etc. But you can only modify it a little bit. Mostly it's decided by the properties of glass. Okay, and just the property of glass is that when you take the double derivative of the refractive index versus wavelength, it crosses 0 around 1300. Okay, so that's. So if you wanted to change this, you have to go to optical fibers which are not made of glass, right? Which people are looking at. People are looking at like these fluoride glasses. So not SiO2, but like these fluoride-based materials. But that's still sort of a field of research. Right. So this EDFA invention was a big deal. And then people sort of made modifications to that to sort of extend the wavelength range. So there's also these thulium doped fiber amplifiers, just like erbium doped. So if you want to go to shorter wavelengths, right? And then there's also PDFA. So this is, I think, praseodymium, which is like a rare earth material. Right, and then people also invented Raman amplifiers, right, which works on this nonlinear optical process of Raman scattering. So we'll also discuss that a little bit in the course, but basically this Raman amplifier is versatile in the sense that you can control the wavelength of operation. Okay, so it requires an external pump wavelength, but by tuning the pump wavelength, you can tune over the wavelength range over which your signal gets amplified. Okay, so basically you can build the Raman amplifiers over almost any wavelength range you want, as long as you have the pump lasers for that, right? So people have shown Raman amplifiers for all this wavelength range or even shorter wavelength ranges here. Okay, so this is optical amplifiers. Right, so basically these are the most sort of important building blocks for an optical communication system, and you can see basically depending on the availability of all of these components, the optical communication technology has evolved over years. And currently, basically, the state of the art is what people are doing is they've developed fibers which are entirely free of moisture, right? So the moisture content is less than 1 part per billion or something. So they've gotten rid of all the moisture, and so the loss profile now looks like this. This peak goes away. Okay, so this is now flat over this entire wavelength range. Okay, so you can call this maybe like 4G. So 4G is basically so these so-called dry fibers. Okay, where the loss is low over this entire range from maybe let's say 1200 to 1600, the loss is let's say less than 0.5 dB per kilometer. Okay, so now we can use this entire wavelength band from 1200 to 1600, right? And for example, using wavelength division multiplexing, so you can have different wavelength channels, each carrying its own data, so that you all send out them parallelly, right? So the total data rates you can achieve now are extremely high. So, right, so current state of the art, people have demonstrated like 10 terabit per second over like up to let's say 10,000 kilometers. Okay, so just crazy numbers, but which are probably required now for the kind of internet traffic that is going on. Okay, so this is included. So this is now with these dry fibers, with WDM, using optical amplifiers. Okay, so putting all of this technology together, we get to these numbers. Okay. So again, to sort of encapsulate the development, if you look at this figure of merit that you saw last time, so which is sort of the data rate times the transmission distance. So let's say in Gbps per times kilometer, right? So if you look at the last sort of 30 years of the last century. So let's say from 1970 to about 2000. Right, so around 2000 was sort of the peak of this telecom boom, where sort of all these components were put together and people were achieving these crazy data rates. And right, so after that, sort of there has been not any fundamental change or action in the technology. Right, people are still looking at different ways to improve things. I had posted a document on Moodle which sort of discusses the roadmap for optical communication going forward. Right, what are the different things people are looking at? So, what's good reading for you guys? But yeah, so if you look at this again, so y-axis. Okay, it goes from 1 to 10 to the 7, right? 7 orders of magnitude. So the first generation systems were somewhere here, so 1970s, right? So it was here somewhere. Second generation systems went like that. Third generation, and then okay. So sort of by 2000 we are able to reach from these kind of numbers. And so after this, you know that basically the growth in the internet exponentially accelerated, and yeah, the traffic over the internet also sort of exploded. What about the receiver curve? Yeah, so for all these 2G, 3G, 4G, right? So we are looking at near IR wavelengths in this range. So for all of them, in-gas detectors are used. Okay. Yeah, so now let's, I said, so nowadays basically we use this entire band from 1200 to 1600, right? So that range of wavelengths is divided into bands. So there is this International Telecommunication Union, ITU. Some people might have heard of. So just like in, for example, the RF spectrum or the microwave spectrum is divided into different bands, right? So you might have heard about the microwave K band or X band or mu band or something. So similarly, this optical communication range of wavelengths is divided into different bands. Okay, so starting from 1260. Okay, so this is wavelength in nanometer. So 1260 to 1360, this is known as the O band. Okay, the next 1360 to 1460 is E band, then S, then C band 1530 to 1565. This is the most widely used range, C band. C stands for, I guess, communication band. So 1530 to 1565, right? So that's where the loss dips to minimum here, even for like the fibers with moisture. So just as a legacy from this 3G networks, C band is sort of the most widely used. Right? Another reason is actually this EDFA, right, works very well in the C band range of wavelengths. So this is the most commonly used band of wavelengths. Then you have L and U. Okay. So this EDFI works well for C band and also L band. If you want to work at other bands, then you have to use these other amplifiers, either Raman or these other types of. So this, if you look at this entire band here, in frequency, that's about 50 terahertz. Okay, so that's sort of the channel bandwidth that you have in your optical fiber. Okay, so if you could, if you develop the technology, you can utilize this entire 50 terahertz channel bandwidth. Okay, so this bandwidth is really huge. Like no other channel actually compares, right? So again, going back to our discussion from the last time, right? We want to define a channel bandwidth where the properties of the channel don't vary too much over the entire band, right? So here, for example, with these dry fibers, the loss is sort of flat over this entire range. Okay. Of course, some other properties like, for example, dispersion, etc., will vary with wavelength, but there are ways to again compensate for that. We discussed. Right. So now, if you look at this in terms of channel capacity, right? So again, you might or you guys should be aware of this Shannon's theorem, right? Which tells you what is the capacity of a communication channel. Right, so this Shannon's theorem says that the channel capacity, which is sort of like the maximum data rate that you can send through the channel, right, is a function of the bandwidth of the channel, right? So here it's 50 terahertz, the bandwidth of the channel. Then a function of the SNR, signal to noise ratio. Right, so you are sending some signal, right? So some signal, let's say, so this is whatever, some voltage or electric field or some quantity as a function of time, you're sending some signal, right? So there is some signal level and then there is some noise level, right? So you have some SNR, and you can imagine that. So for example, you know that nowadays basically we work only with digital data, right? So basically what is done is you sample this whatever signal you have at certain time intervals, right? And now again there are requirements on what should be the sampling rate, right? So there is this Nyquist theorem that you need to sample at a rate at least twice the maximum frequency of the signal, right? So anyway, so you sample the signal, so you get a set of points time, and then for these points, now you quantize them, right? So you convert them into numbers, and the quantization that you can do, so you can have any number of levels that you specify, right? So if you quantize over m levels, that is like having log m bits, log m to the base 2 bits, right? And the number of levels you can quantize depends on the noise, right? So the minimum separation between two levels has to be more than the noise, right? Because I mean the signal can fluctuate by amount proportional to the noise. So the separation between the two levels has to be more than the noise, so that when there is some noise on this, we still quantize this at this level, not the next one, right? So higher your SNR, right, which means higher the signal level compared to the noise, the more levels I can quantize it into, right? Which means I can send more bits, right? So for each symbol here, if this m is higher, right? If SNR is higher, m is higher, and I can log to m the number of bits that I send per symbol is higher, right? So that is what this thing is. This factor is good, right? So multiplying by the bandwidth, this is giving you some sort of spectral efficiency, right? How many bits per symbol I can send, right? So equivalently, if you bring it this side, right? So then this data rate divided by this becomes like bits per second per hertz, right? So this is something like channel. This is like spectral efficiency, which is just depends on the SNR. Okay, anyway, so if you put the numbers here, right? So delta F channel is 50 terahertz, right? We put some typical number. Let's say we work at an SNR of let's say 20 dB, right? Which means the signal power to the noise power is 100, right? So again, hopefully you are also familiar with dB, right? So SNR in dB is 10 log 10 signal power divided by noise power, or in terms of amplitude, 20 log 10 signal amplitude by noise amplitude, right? So this could be like electric field amplitude, for example, or voltage or something, right? So let's say if you work at 20 dB SNR, then this Cmax that you get, right, this comes out to be 350 terabit per second. Okay, so this number is in some sense like the absolute maximum. If you utilize this entire band efficiently, what is the maximum data rate that you can send through a fiber is that number. Okay. Of course, we are sort of maybe an order of magnitude or two lower than that currently. That's because not the entire band is utilized efficiently. Okay, so anyway, these numbers are much bigger than for any other type of communication system, right? And to utilize this SNR gain, right? So basically, to increase the spectral efficiency or bits per second per unit bandwidth, you also need to use sort of sophisticated modulation techniques, right? So, for example, the simplest modulation technique you can use is just on-off key, right? So that's called OOK, on-off key. So that's just you send a pulse for bit 1 and nothing for bit 0. Right, so you have a pulse of optical pulse of some duration, PB, which signifies bit 1, and bit 0 is you send nothing. Right, but here you can see that sort of the spectral efficiency here is roughly like 1 bit, right? 1 bit per second per hertz. Right, so the bandwidth of this pulse is sort of 1 over TB, and I'm sending 1 bit per TB duration. Right, so the data rate divided by the bandwidth that this is utilizing, this comes out to be about 1. Right, so for the simplest modulation scheme, the spectral efficiency is only roughly 1 bit per second per hertz. Now, if you want to increase SNR and increase your this channel capacity, you have to go to a different kind of modulation, because with this modulation, you are not even if you increase SNR, you're not maximizing the spectral efficiency. You're still ending like 1 bit per second, right? Another way to see it is that basically for this kind of communication system, an SNR of 1, anything more than 1 is enough, right? Because for 0, I'm not sending anything. For 1, I'm sending something. So that if the noise is less than the signal amplitude, right? If the maximum noise is less than the signal amplitude such that with the noise this thing remains above 0, then I can still distinguish bit 1 from bit 0. Right? So that's what, like if you put SNR equal to 1 here, you get this is equal to this, right? Or this is 1. So that's what this simplest on-off keying modulation scheme is utilized. So even if you increase SNR, the way this works, it's not really taking advantage of the increase in SNR, right? But what you can go to other kinds of modulation techniques where you can utilize this SNR gain, right? And you know there are various kinds of coherent modulation schemes that you have probably studied in electronic wireless communication, for example, right? So there are phase shift keying, right? So there are, again, this M is sort of the number of bits per, or this M is basically the number of levels, right? So for example, you have 2 PSK, 4 PSK, 8 PSK, or 16 PSK, and then log of this number gives you the number of bits you are sending per symbol. There's also an QAM, quadrature amplitude modulation, right? So here you're modulating the phase, right? So here you're modulating the intensity or the power. Here you're modulating the phase. Here you're modulating both amplitude and phase. Right. So anyway, if you look at the state-of-the-art modern day communication systems, they are utilizing some sort of coherent modulation scheme to take advantage of this SNR. Right. So optical systems, for example, they are using like 16 QAM or even higher sometimes. But you'll see in the course, like these kind of modulation techniques are more complicated, right? So they require more complicated detection, also more complicated transmitters, but also more complicated detection. Whereas this one is very simple in terms of detection. Okay? So again, as a legacy from like third generation networks. So what happened like around this third generation thing, like around 1990 to 2000, that decade is basically a lot of optical fiber was laid down all across the globe. Okay, so thousands and thousands of kilometers of optical fiber was laid down. Like there was this telecom boom, and basically what ended up happening was not all of it was utilized. Okay, so basically people are still trying to utilize the fibers laid down already, and sort of a lot of the technology which was laid down already for the third generation. So still, like if you look at the commercial internet traffic, most of it is simple OOP modulation. Okay? But slowly people are sort of trying to replace them with these coherent modulation techniques. Right, so if you look at sort of the current standards for optical communication, so the kinds of data that is usually sent is, right, so you have like maybe some audio signal or some video signal, right? That's sort of the signal you, like any other type of text or document that is sort of low bandwidth requirement, right? So video is sort of like the highest bandwidth hungry signal, right? So the current standard is that basically for on one wavelength channel, right? So on one wavelength channel, we send about 40 gigabit per second, right? And now this number is coming from the electro-optic modulator speed. Right, so in the transmitter you have a laser, and then you have an electro-optic modulator, basically which is converting your electrical data that you have stored, and you want to send it through optical means, right? So this electro-optic modulator is converting the electrical data onto the optical waveform. So the speed of those modulators are sort of limited to these speeds. Okay, so that is what deciding how much data I can put on one wavelength channel. People are still working on sort of enhancing these speeds, and nowadays people maybe go up to 100 gigabit per second, but this is sort of roughly the standard, 40 to maybe 50 gigabit per second on a single channel. Right, but this is still a lot of data, right? So for example, if you have, if you look at a video, typical video signal like a VGA video or something. So this is like, I don't know, 800 by 600 pixels with some 16-bit quantization for each pixel, right? And then I think maybe 30 hertz refresh rate. So if you calculate, that comes out to be about 155 megabit per second. Okay, so to transmit this kind of video quality, you need 155 megabit per second. Right, so now a single wavelength has a capacity of 40 gigabit per second. So you can see that this, now we can send 256 video channels. Right, so this divided by this gives you 256. Right, so for example, if you nowadays, a lot of providers are providing this fiber to the home, right? So you get fiber right up to your home, and then you can get cable TV and internet and whatnot, right? And so roughly the number of channels that you can get is like that, because typically you get only a single wavelength channel up to your home, and then right, so you can see that those are the kind of numbers we are talking about, right? So this standard is called STM256, because you can send 256 video channels simultaneously on one optical video. Okay, and how these are done is basically time division multiplexing, right? So how different, for example, different video channels are sent on the same optical wavelength is through time division multiplexing. So from here you see that the bit duration is about 25 picosecond, right? Just 1 over this. So that's the bit duration for the optical waveform, right? So this the bit duration is 25 picosecond, right? So you have 1 pulse per bit duration. And so now if you look at this 155 megabit per second, right? So this video bit period corresponding to this data rate, right, is 256 times this, right? So it's like I don't know, 60 something nanoseconds. I don't know exactly something, let's say 65 nanoseconds. No, or 6 nanoseconds. So about like 6.25 nanoseconds. Right, so for a video signal, basically I only have 1 bit every 6.25 nanoseconds. Whereas for the optical channel, I can send 1 bit every 25 picoseconds. So what I do, so this first bit I send for channel number 1. This is n equal to 1, and then after 6 nanosecond will be the next bit for the first channel. Okay, and then the next optical bit will be the first bit for the second video channel. Right, and then similarly, after 6.25 nanoseconds, this will be the second bit for the second video channel. And now you have the third set, right? So you'll have 256 video channels. So 1 bit for each channel, then the second bit for each channel, like that, right? So this is basically time division multiplexing. Right? So that's how data is sent currently on the optical fiber. So simple on-off keying modulation, and then time division multiplexing. So these kind of networks are known as SONET, so synchronous optical networks, or sometimes SDH, which is synchronous digital hierarchy. Okay, so they go by different names in different places. Like in the US, they might be called SONET. In Europe, they're called SDF something. But the idea is basically this time division multiplexing of different electronic signals that you want to send onto the optical waveform. Right, so that's for one channel, and then if I want to now send even more data together on the fiber, what I do is do WDM, right? So I utilize different wavelengths. Right, to get up to these terabit per second speeds, what is done is, so one channel gives me 40 gigabit per second. So then I have multiple channels here, wavelength channels. So, right, so, and they are separated by 100 gigahertz. Okay, so each wavelength channel is separated by 100 gigahertz so that it can accommodate a data of up to let's say 50 gigahertz, 50 gigabit per second. Right, so now I have multiple wavelength channels, right? So lambda 1, lambda 2, 3, lambda 4, each is separated by 100 gigahertz. So if the center wavelength is let's say 1515, the C band, then in terms of wavelength, this separation comes out to be about 0.8 nanometer. Okay, so you can, for example, the C band, which runs from 1530 to 1565, right? So this 35 nanometer bandwidth, you can partition it into 0.8 nanometer slots. So you can see you'll get 44 channels, right? All separated from each other by 0.8 nanometer. Right, so now for example, you can send 44 into 40 Gbps will be your total data rate now, if you can send all 44 channels together. Okay, so yeah. So this grid of wavelengths separated by 100 gigahertz or 0.8 nanometer, this is called the DWDM grid. So it's called dense wavelength division multiplexing. Dense because basically the wavelengths are as close together as possible, right? Because if they are closer, then basically the data from neighboring channels will interfere, right? So this is the densest allocation of wavelengths that you can have. So it's called dense WDM, DWDM. Okay. Yeah, so I hope that sort of encapsulates sort of where we are in terms of how optical communication systems work sort of in the modern day. And so we'll learn, in the course, we'll learn about each of these aspects in more detail, right? The fiber channel, transmitters, amplifiers, receivers, different modulation formats, WDM, what are the different impairments that can happen. So we'll study various aspects in more detail throughout the course. Any questions on sort of general introduction so far? Okay, so let's briefly just talk about some system of units that we'll be using throughout the course. So bandwidth is of course an important quantity in communication systems, right? So bandwidth is basically a range of frequency, right? So it has units of frequency typically, but in the optical case, frequency is also related to wavelength, right? So in terms, for electronic communications, RF micro, usually we don't talk about wavelength that much, but in the optical case, you've seen already that we are talking about wavelengths quite a bit, right? So many times the bandwidth is defined. So if you take the derivative on both sides, then right, and so if I look at the magnitude, this will be like that, right? So the bandwidth in frequency which you are used to, hertz, is related to the bandwidth in wavelength units here, which is typically measured in nanometers. Okay, so for example, we saw, like, so if you see here, right? So one thing first to note is that the bandwidth in wavelength units is not a fundamental quantity in the sense that it depends on the center wavelength, right? Because we are getting a factor of c over lambda square here, so it depends on what lambda you are at. Right, so again, if you look at this DWDM grid, if I take delta F to be 100 gigahertz, right, this center wavelength to be 1550 nanometer, C is right, so you just calculate, you will get this delta lambda to be 0.8 nanometer. Right, so the same 100 gigahertz now, if I go to a different wavelength, let's say 1.3 micron, then this delta lambda would be different. So that's one thing to keep in mind. This delta lambda, so the bandwidth in wavelength units depends on where you are in wavelength space. Whereas frequency bandwidth is like a fundamental quantity. But in many places in optical communications, we'll sort of freely switch between these two. So keep in mind how they're related and depends on which wavelength you are working on. Okay, so that's bandwidth. Then power. So typically here we only be talking about optical power. I mean, we'll be talking about electrical power when we talk about photodetectors, etc. But otherwise, mostly we'll be talking about optical power. So, I mean, of course, you know, SI units of power are watts, but in optical communications, frequently we use these dBm units. Okay, so these are decibel units normalized to the small m stands for milli or milliwatt. Okay, so basically the power in dBm is the decibel, which is 10 log 10, of the power in milliwatt. Okay, or equivalently you divide the power you have by 1 milliwatt and then take the decibel. Right, so for example, if you have 1 milliwatt of power, that corresponds to 0 dBm. Right? So you can see, like, for example, 2 milliwatts is like 3 dBm, 10 milliwatts is 10 dBm, 1 microwatt will be minus 30 dBm. Okay, so in dBm units, power can go negative, right? It can also be 0. So why do we use this dBm units? That's because it becomes easy to sort of, so let's say you have a long communication link with a lot of components in between, right? And each component is giving you some amount of loss, okay? Or some amount of gain, let's say you also have amplifiers. So it's easy to keep track of all of them if you just, for example, measure them in dB units, right? So this particular component gives me this much amount, this much dB of loss, or this much dB of gain. Then you can just add all of them up in dB, and basically that will give you the difference in the power in dBm units. Okay. So let's say you have a link like this, for example. So you have the transmitter here, okay, and then you have some length of fiber. Okay, then you have some amplifier in between. Then you have another length of fiber or something. So let's say you have some loss here. So you have 9 dB loss, right? So loss or gain in dB, you know how to measure, right? So let's say the amplifier gives me like 14 dB gain, and then again another length of fiber after that gives me like 8 dB loss. And so let's say my input power here is 1 milliwatt. What is my output power here? Right? If we calculate in dB units, it's very straightforward to do. So the total loss here is 9 plus 8, 17 dB. Total gain is 14 dB. So there's a net loss here of 3 dB. Right? So this is the power here. There's a loss of 3 dB from here. So if I convert this to dBm units, so this is 0 dBm. So there's a loss of 3 dB. So here it will be minus 3 dB. Okay, so I can just add up all the losses. Otherwise, you know that in natural units you have to take this exponential e to the minus alpha L and whatnot, right? So the calculation, this way it's easy to keep track of everything in straightforward. So that's why I use dB units. Yeah. So again, so loss or gain of any component is measured in dB. So that's like 10 log 10 P out divided by P in. So the power going into a component and power coming out of a component, you take the ratio and then take 10 log 10, you get dB. Right? So if this is a positive quantity, that's gain. This is negative, then that's loss. Right, so continuing on this dB theme, why on-off key cannot be used for increasing spectral efficiency? So there's a question. So we discussed this OOK scheme, and we said that basically the spectral efficiency is just 1 bit per second per hertz, right? I mean that's just the modulation. I mean you could have variation. Right, so there is something called, for example, pulse amplitude modulation, right? So again, like you could have m levels. So then what you could do, you could have different levels, right? So you have 4 levels here. So now you could send 2 bits per bit duration. So now your spectral efficiency is 2. So this is a variation of the on-off keying, but if you just have on-off keying, that's just like you have 0 and 1. So by definition, its spectral efficiency is 1 bit per second. Right, and it's independent of the SNR because so you have some noise on this, you can see, right? So a high SNR means like this is very small, it's just very nice like this. 1, 0 is well separated. A large amount of noise means that the separation becomes lower. But you can see that as long as the SNR is more than 1, I can always distinguish between 0 and 1. Okay? So that's sort of, as long as the SNR is more than 1, it works and you don't really gain by increasing the SNR. Right? So to make use of the increased SNR, what you can do is, for example, now divide this like this. Right? So now if the noise is lower, such that the noise amplitude, right, is smaller than, let's say, 1/4 of the maximum bit amplitude, then you can divide this into 4 levels. Anyway, but whatever you do, you have to make transmitters which sort of encode your electronic data onto the optical format like that, and then at the receiver you have to decode it. So there's a trade-off. So this is the simplest thing you can do, just on-off keying. And basically, because all the other properties that we discussed of the optical communication system are so much better than the electronic systems, right? So even with on-off keying, people are able to get very good performance. So only if you want to push to the limits, then you go for higher modulation formats. Anyway, I hope that's clear. Yeah, right. So yeah, so then there is this fiber propagation loss, right? Alpha. That so we already discussed that in a couple of graphs, and we saw the unit for dB per kilometer. Right. So again, there we have used dB units again to sort of be in line with these dB units for power and loss and gain, so that we can easily sort of calculate the total loss and gain and the powers in an optical link. Right. So you know that. So there's some propagation loss for the fiber alpha, right? And in natural units, basically, so if this length is L, then you know that there's an exponential relationship, right? So the power decays exponentially with length, where now this alpha is the loss coefficient, right? So the natural units is per length, so right, per kilometer or per meter. But again, if we want to calculate in dB units, what we do is convert this. So you say the propagation loss in dB units, so dB per length is basically we take this formula for the loss, right? So what would be the loss? 10 log 10 of the ratio of the input and output power. For loss, P in will be more than P out, right? So if you want this to be a positive number, then we take that. Right, so this gives me the total loss over the length L. Right? So now per unit length, I just divide by L. Okay, so that's how I define the loss in dB per kilometer. So I take the loss in dB and then divide by L. Right? And this P in and P out are related like this. Right? So if you put in this formula here, you can see that there is a numerical relation, a linear relationship between this alpha in dB per kilometer and then just the natural alpha in per kilometer. Right? If you put the numbers here, so L will come out and then cancel with this L. So this, and then you'll have a log 10 of E, the alpha. So this comes out to be about 4.34 times the alpha in per kilometer. Okay. Yeah, so that's the relation between the usual alpha that you might have seen, for example, in physics, or to this alpha and dB per kilometer. Right. Again, now the advantage is that if we know the fiber loss in dB per kilometer, then the total loss of the fiber for any length L is just this alpha in dB per kilometer times the L, right? In kilometer. So again, like if I have 0.2 dB per kilometer loss, I have 100 kilometers of fiber, then the total loss is 0.2 times 120 dB. Right? I don't have to take exponentials. Right? So for given some length of fiber here, I can straight away write what is the loss in dB. Right? And then calculate my budget. So yeah, you have to be very comfortable with these dB units and this change between frequency and wavelength. Okay, so yeah, so last thing we discussed today is this sort of a block diagram of the optical communication and communication system that we discussed, right? And then we'll see what are the components in each of these blocks for an optical communication system, and then basically during the course we'll discuss each of those components in some detail. Right, so again, if you look at any communication system, there's a transmitter, channel, and receiver, right? These are the main blocks. So for an optical communication system, basically, you start with some electrical data, right? So it's, for example, stored on some server or some hard drive or something, and then you want to send that some information somewhere else, right? So the first thing that's done is you use some optical transmitter to convert this electrical data to optical data, right? And then send it over the channel, which is an optical fiber in our case. And then you have an optical receiver, which is basically a photo detector plus some circuitry, right? And then you decide based on the electrical waveform that you get, like what data you have. Like you decide the bit stream and you get your electrical data out. Right, so if you look at each of these, so for example, if you look at the optical transmitter, basically, so you have an optical source, right? So this is some light source. So for example, this is nowadays we only basically use lasers, semiconductor lasers. In the first like 1G, 2G systems, LEDs were also used. Even nowadays for shorter distances, like for example, within data servers or within local metro network, like below kilometer scale, LEDs can still be used because LEDs are much cheaper than lasers. So you have some source which, so these sources again are based on semiconductor technology and they are electrically driven, right? So you have some electronic driver. So either you can directly modulate the electrical current into these devices, right, to imprint the electrical data, but that is limited up to some speed, like let's say 1 Gbps is sort of the maximum data rate you can get with direct electrical or current modulation. If you want to go higher, then you use external modulators, so electro-optic modulators. Right, so this electro-optic modulator has two inputs. One is the optical input. So this is just a continuous wave laser, right, always on. And then the other input is the electrical data that you want to send. Okay, and then depending on this electrical data, this modulator, so you might have studied about some of this or are going to study maybe in your optical electronics course. Right, so here you have some lithium niobate device whose refractive index you can control with voltage. Right, so basically you make this device such that this electrical data now is imprinted onto the optical. So you can, depending on your modulation format, you can build different modulators. So for example, you can have an intensity modulator, which according to the electrical data will now have your optical waveform. The intensity or the optical power will vary like electrical data, or you could have phase modulators, where you only change the phase. So the intensity remains constant, but the phase is now imprinted with the data. Or you could have combinations like QAM or other more complicated types of modulation. But yeah. Right, and now for these modulators, external modulators, lithium niobate based modulators, you can go up to like 50 gigabit per second. That's sort of the current state of the art. Right, and then after this, you have some like fiber optic coupler or connector. So you plug a fiber in basically from here and then go into your channel. Okay, you also have pigtail devices, basically where all this is sort of packaged into one single device. Right, so again, so this modulation, basically the electric field of the optical wave, right, so this is the electric field of the optical wave, right, or amplitude basically. So mod square of this will give me the power in the optical field. So right, so this is a vector quantity, right? So there is some direction, right? So this is polarization, right? Which direction the electric field is pointing in. Then you have an amplitude, right? And then basically frequency and phase like this, right? So this is coming out of the source, like let's say you have a laser source, and so this kind of field is coming out of the laser. Right, and now I have electrical data, which is a function of time. So, which I want to imprint on this. So, I can choose various things, right? So, for example, I can make this a function of time like this. So, that would be amplitude or intensity modulation. Right? I could choose the phase to follow my electrical data, so that would be phase modulation, right, or phase shift keying. Or I could choose this frequency, that would be frequency shift keying or frequency modulation. Or I could even do polarization for 2 bits, right? So I have horizontal and vertical. I could do 0 and 1 like that. So there's a question, adding the EO modulator adds loss. Yes, it does add loss, but it's not a very large amount of loss. So there is some connection loss here, and then there's some insertion loss here, but typically, let's say that's a few dB. Okay. You can always have like an amplifier here. You put an optical amplifier. It's called a booster amplifier. To compensate for all the losses. Okay. So the insertion loss is not too much of an issue. But yes, it does add a little bit of loss. Yeah, and then depending on the modulation format, there is some modulation efficiency for these devices, right? So like for a particular level of voltage, it will impart a particular amount of phase, etc. So that depends on the design of the modulator. Which, yeah, again, more details of that probably you learn in the optical electronics course, how these modulators are built. But for our purpose in this course, we just take it as a black box device. It does the function that. Okay, so yeah, so as I said, the most common thing that is done in practice is just this amplitude, or it's called amplitude shift keying, or just intensity modulation, or on-off keying. But you can also do so. We'll towards the end of the course we'll study other kinds of modulation techniques with these other parameters. Right, so that's about the transmitter. And then in the channel, of course, you have a fiber, right? But typically for very long distance communication, for if you're again communicating over, let's say thousands of kilometers, then you can't just have one fiber because the loss becomes too large. So typically what is done is, typically let's say you have a 50 to 100 kilometer length of fiber, and then you have an optical amplifier. Okay, and then another length of 50 to 100 kilometer, then another amplifier, and so on. Okay, so your channel consists of optical fibers and amplifiers. So as we discussed last time, the fiber only introduces loss, right? So only the amplitude of the signal goes down, but there is actually no noise added, right? There is no external interference, or there is no other mechanism which is contributing noise actually. So actually the fiber, what it does is it introduces loss, but actually it doesn't introduce any noise, as we discussed last time, right? In that sense, the fiber is sort of like perfect channel, there is no noise. But because we have to put optical amplifiers for very long distances, you know that any amplifier introduces noise, right? So whenever we amplify a signal, we don't get that for free. Any amplifier automatically fundamentally adds noise. Okay, so basically the noise in an optical channel is coming from amplifiers. Okay, so the channel has two characteristics. One is loss characteristics, which is coming from the fiber, and then noise characteristics, which will mainly come from the amplifier. Right. And then finally, we go to the receiver. Right, so the receiver, basically you have your fiber coming in, right? So then you have a connector or something, a coupler, and then you have a photodiode. Right, so again, this is also made out of the same C5 semiconductor that this source laser is made out of. Right, again, so this requires some electronic driver or bias. Right, and then you get an electrical current out, right, which is basically hopefully reproduces your input data. Right, and then because this current will now have noise, and also the level will be small because of all the losses. So now you have like various electronics here, like electronic amplifier, filter, equalizers, right? And then you do some threshold detection. Right, so you get waveforms like this, and you say, okay, if it's above this level, then I say bit 1. If it's below this level, I say bit 0. Right, and then you get your bit stream. Right, so you can see that whatever data rates I am operating at, so let's say this is 40 gigabit per second, your photo detector also has to work at those speeds, right? Because it has to now produce a current which is varying at that speed. So the photodetector bandwidth has to be at least the modulator bandwidth. Okay, yeah, and the simplest, again, the way communication is done is using this amplitude or intensity modulation. And in the intensity modulation case, you can see that I can directly detect, right? Because the optical power is varying here. And so basically, whenever the detector receives high optical power, it will give me a high current. When it detects low power, it will give me a low current, right? So that's called direct detection. I don't have to do anything extra. I just directly put in the optical signal and it gives me the electrical output. Okay, so this is called, so here it's called intensity modulation, here it's called direct detection. So this link is called IMDD. Okay, intensity modulation direct detection, which is the most simplest form of the link. But yeah, you can also use other modulation techniques. For then your detection will become more complicated. Right, and finally this whole link is characterized in terms of some metrics, right? So the main thing that is seen is called bit error rate, right? BER. So this also you know from probably electronic or wireless communication courses, right? So how many bits are in error? So typical metric to aim for is like 10 to the minus 9 or lower. So for optical links, that's sort of the figure one aims for, 10 to the minus 9. So 1 out of every billion bits are in error. Okay, so basically, yeah, in the course we'll take up each of these components, right? So these three main blocks, and then each block we'll discuss each of the components in some detail. That's sort of basically what the course is about. Okay. So first we'll start with the channel, right? And we'll discuss properties of the optical fiber and how it can impair basically the optical signals propagating through it. So that will be the first part, and then we'll go to transmitters and receivers and amplifiers and sort of put them all together.